Okay, so let's recap what's the process of set removal is. So set removal or presetting is the process used in manufacturing a spring to induce the use for reduced stresses. Okay, and the spring is made longer than needed, then compressed to solid height, intentionally exerting the yielding stress. This operation sets the spring to the required final free length, and yielding reduces residual stresses opposite in direction to those induced in surface. And the 10 to 30% of the initial free length should be removed. And set removal is not recommended when springs are subjected to the fatigue. Okay, so I'm going to explain what's this the tax meaning. Okay, so when we manufacture spring, okay, so we have the spring wire, which is wounded with a rotating mandrel. Okay, so when this mandrel rotating and this spring wire is subjecting to bending, right? The bending will create the normal stress, right? Within this cross section of this spring wire. And this normal stresses from bending is residual stress. And these residual stresses are different from the shearing stress from the compression, okay? The compression of the spring. Okay, the two different things. Okay, so how to evaluate the shearing yielding stress? So first we have to take two parameters into account. First is the SUT, which is the minimum tensile stress, and the SSY, okay, which is the shearing yielding stress. Okay, of course we have to uh, also consider, what's the target material property that you need, that you require, like the materials property or the spring index, the wire diameter, and so on. Okay, and these two parameters uh, are the keys to evaluate uh, when this springs is subjecting to the static loading or dynamic or fatigue. Okay, and also the set removal process. Okay, so and let's recap what we learned previously. Okay, so the compression of the spring causes the shearing stress, right? The shearing stress is equals to uh, the first term represents the compression from the torsion, right? And the second terms represents the direct shear, okay, the pure shear, okay? Right. Okay, so we can just combine this with a constant KB, right? So we can just convert it for this shearing stresses uh, represented as the shear stress equals to the constant KB times this term, okay? Okay, and the compression do not cause the bending, okay? Do not cause the bending of the wire, okay? Do not cause the bending of the wire, okay? Okay, so how to evaluate, that's what I mentioned previously, how to evaluate the minimum tensile stress, SSUT, which is a function of D, A, and M. D is the diameter of the wire, right? A and M are the parameters depends on the materials. Okay, depends on the materials, and which can be look up in the textbook or handbook. Okay. So therefore, say the A and M parameters are materials coefficients. So we can find it online or textbook or any handbooks. Okay, any handbooks. And so how to evaluate these two parameters from experiment, right? From experiment. So the SSUT is the tensile stress, right? And the diameter that we already know if we decide, if we are the engineers or we are the designers for the spring, so we can select what the diameter of the wire is, right? So we know the diameter, right? And we can get the tensile stress from the experiment. right? From the experiment. Therefore, we can get the experimental plot like this. Okay, so we can get the, okay, so we have the many experimental data point here, and which can be fitting as a linear function. Okay, as a linear function. Okay, after log plot. Okay. Okay, so we can define this linear function from experiment. Okay, from experiment with the linear equation, right? Y equals to mx plus b, right? A constant. Okay, and this is the slope, right? Minus, okay, minus sign. Okay, so we can just uh the both side, we can just logarithm of the both sides, right? So we can get this equation and we can keep calculating it. Okay. Okay. I think it's quite it's very fundamental high school mathematics or college mathematics. So okay, so finally we get the SUT, okay, equals to this term. Okay, right? So we from this linear equation, right? This term is the y. So I just claim all of them. Okay, so this term present y, right? And m and x and the constant, right? The intercept. Okay, therefore, we can just manipulating this equation to figure out the SUT equals to this term. Okay, and then we define the exponential part of b, right? Is the constant, is the parameter a. Okay, is the parameter a. Okay. Okay, and this term, right? You can just eliminate it. So we get this first term is the d, the part of minus m, minus m. Okay, so we can just rearrange this. We can rearrange this equation. So the SUT equals to a over d part of m. Okay. Okay. So based on the minimum tensile stress, we care only about the elastic limit, but not fracture. Of course, we will fabricate the springs. We want it fracture, right? So we have to evaluate the parameters A and M in the elastic limit. Okay, elastic limit. Okay, so we can find the intercept and the slope M. Okay, the B and M. Okay. Okay, so let's just think about what's the relation between the shear stresses and the shear yielding stress. Okay, SSY. Or we can say the shear yielding stress represents the torsional yielding stress. Okay, so we can roughly estimate it, the SY, which is the yielding stress by tensile test. Okay, in between of the 0.6 SUT and 0.9 times SUT. Okay, and the SSY, which is the shear yielding stress or torsional yielding stress, equals 0.557 times SY, the yielding stress. Okay, so this comes from the distortional energy method. Okay, distortional energy method and the von Mises stress. Okay, so you can recap what you learned previously. Okay. Okay, so if you still remember this relation when we design a shaft, the sigma prime is the von Mises stress equals to the square root of the sigma square plus 3 times tau square. Okay, and the sigma here is the principal stresses, and the tau is the shear stresses. Okay. Okay, so you can just recap this. Okay, it's the uh comes from the torsional energy method. Okay. Okay, so therefore we can plug this number this 0.556, right? Right, SSY, right? 0.55 y, and therefore this SSY, the torsional unit stress equals to the 0.556 times 0.6 times SUT, and less than the 0.556 times 0.9 times SUT. Okay, so we can figure out the torsional unit stress if we evaluate the torsional unit stress based on the ultimate tensile stress, or say the minimum ultimate tensile stress, and this SSY within the range of the 0.35 SUT and 0.52 SUT. Okay. Okay, so, and then how to find the SUT, you can check the table. Okay, we can check the table. For the in the elastic limit, the percent of the SUT, the percent of the SUT with the tension, if it's with the tension. Okay, so for this music wire, okay, so with elastic limit is about 65 to 75% of SUT. Okay, so with the torsion, so it's the springs under the torsion, the elastic limit is about the 45 to 60% of the SUT. Okay, so it depends on the different materials and with the different elastic limit. It is could be the tension or torsion. Okay, could be the tension or torsion. Okay. Okay, so what's this for? I mean, why we need to find this SSY, the shear unit stress? What for? Of course, it's for evaluating whether it's in the elastic limit, right? So we have to use it as the design factor. Okay, so when this spring is subjecting to static loading, okay, or when the number of cycles load, okay, so right, so we have to consider the SSY. And when this spring is under dynamic or cyclic loading, or say the fatigue, right, we still have to consider the SSY. And of course, and this we have to if this spring is processed with the set removal, and we have to use the SSY to evaluate its plastic deformation. Okay, plastic deformation. Okay, therefore, we can say the set removal process causes the plastic deformation to induce the residual stress, which is offsetting the surface stresses. Okay, so therefore, if you still remember, the set removal process is not suitable for the cyclic loading or say the fatigue. Why? Because the residual stress from set removal is opposing in the surface stresses direction. Okay, so if this loading is cyclic applied to the spring, that means the spring either way it will meet the stress direction is the same as the residual stress, right? So that will create the superpose condition. That means the spring is subjecting to the double higher stresses. Okay, double higher stresses. Okay, so let's look into the set removal process. So for this fabricated initial lens, okay, so this is the initial lens, okay, and we apply a force, okay, we apply a force, right, to compress this fabricated spring in the solid lens. And then we release the force. And this lens, the new lens L0, which is shorter than the initial lens. Okay, which is shorter than the initial lens. And this force causes the plastic deformation. Okay, plastic deformation. So in the very beginning, we mentioned that when the compression applied to the helical spring, right? So there's the torsional shear and the direct shear, right? Applied to the cross section of the wire. Okay. So the similar, we have the torsion, right? Applied to the spring. Okay. So if we look into the cross section, okay, here the cross section, we call this cross section, right? Just look into this cross section. There's some region which is still elastic behavior, and there's some regions are already in the plastic deformation when the force compressed. Okay, so remember this force causes the plastic deformation. Okay, plastic deformation. Therefore, if we look into this, the cross section of the wire, some region basically is the center region of the spring wire, which is still elastic. Okay, and the ring, the outer region start to deform plastically. Okay, so some regions still remain in elastic and some regions are plastic deformation. Okay, so during this torsion, so this is stress distribution here, right? So it's stress distribution here. Okay, and then there are some stresses causes from the torsion is beyond the SSY, the torsional yielding stress. So there's some stresses already beyond the SSY. That causes the plastic deformation. Okay, that causes the deformation, plastic deformation. Okay. Okay, so therefore, if we plot the stress and strain curve, okay, so this yellow curve present this elastic behavior, right? So when we apply the force within this range, when we release it, it will return, right? This strain will return to its original point, right? So when this force is beyond this elastic limit, suppose here, and we release the force, right? And the strain will return to a certain point, which has the permanent strain, okay, permanent deformation. Okay, and so on. We can apply the higher stress and return. So the permanent strain will be higher. Okay. Okay, so during this permanent deformation, when the force released, that means the force equals to 0, right? The spring will return to a new free lens, right? Because it will not directly return to its original point, right? It will return to here, here, here. This depends on the force you apply. From this permanent deformation, or say the plus deformation, shorten the length of the spring, create a new free length. And this stresses is good. It's good. But it's good for static or for the low cycle. Okay, low cycle, low cyclic loading. Okay. Okay. And the maximum allowable torsional stresses, sorry, it's SSY, is a function of SUT. Okay, it's a function of the SUT. Okay, if the spring is before presetting, suppose the spring wire is not processed in the presetting. Okay, and whose SSY is roughly equal to the 0.45 SUT. And if this spring wire is processed with presetting, or say the after presetting, whose SSY well is equal to the 0.65 SUT. Okay, so they're different. The torsional unit stress is highly depending on whether it is presetting or not, right? So before and after. So you can see the stress is much higher, right? It's much higher after set removal process. Okay. Okay, so and there's one example that's finished this example first. There's a spring wire. Okay, so the diameter is as 0.045 and its shear rigidity is here, and the name of the coil is 9, equals to the active coil and the total coil. So when this deflection, when the force applied to it is 5 pounds, and the y deflection is equals to ½ inch. Okay, and what is the diameter? And what's the n? Okay, the safety vector. Okay, what the safety vector is. Okay, so we just show you the fundamental calculation of the compressive spring, helical spring. Okay, so if we have the spring constant, right? So we know the force and the deflection, the force and deflection. Therefore, we can find the K, right? F over Y, F divided by Y is equal to 10. Okay, the 10. Okay, the K spring constant. And also the spring constant, if we consider its materials property and the dimension, the K equals to the D power of 4 times the G over AD cubed times NA. Okay, so this K is evaluated by the materials property and the geometry or the dimension. Okay, so we can rearrange this equation, extract the D, right? The mean diameter, okay, here. Okay, and then we plug those numbers that we already know, like the diameter, right, of the wire, and the shear rigidity here, right, and the K we find here, and the active number coil. Okay, therefore find the diameter, the mean diameter of the compressive spring equals to 0.507 inch. Okay, and the tau max, the maximum shear stress equals to KB, the constant, right? Okay. Okay, so the KB we already know equals to this term, right? Okay. So we can plug in those numbers that we already know. Okay, so where's the F F max. F max. So the F max equals to the K, we already know the spring constant, K, times the Y max, the maximum deflection after the force applied to it. Okay, and the Y max, the maximum deflection, equals to the L naught, right? The L naught, the new free length minus the solid length. Okay, and we know the L naught is equal to 2 inch, right? And the solid length equals to the N times the NT plus 1 equals to 0.45 inch, right? Therefore, we can figure out what is the Y max is. This is the 1.55 inch. Okay, therefore, we can plug those number to this previous to the previous equation. Okay, the Y max and the F max and the Y max. Okay. Okay, so the Y F max here. Okay. Okay, so finally we get the tau max, the maximum shear stress equals to 203 KSI. Okay, 203 KSI. And as well we mentioned previously, the SSY equals to 0.6 times the SUT. Right? Therefore, the SSY roughly equals to the 189 KSI. Right? Okay, so and then we can evaluate the safety vector, right? Here, the SSY equals to 189 divided by the tau max. Okay. Okay. And how to get SUT? We have to find the A and M parameters by checking the textbook or any mechanical handbook. Okay, so this is the table that we need to check. Okay, right here. The A equals to 201. Okay. Right here. Right. So this is what the materials we are using. And the exponent M equals to the 0.145. Okay, so plug these two numbers. Okay, this number and the 201 to here and here. So we get SUT equal to 315. So we plug in here, we get SSY equals to 189 KSI. And we just plug this number, right, to here, divided by the tau max. Therefore, we get its safety vector. Okay, we got its safety vector. Okay. Okay, and here are some parameters for those spring wire. Okay, for those spring wire. Okay. Okay, so we're gonna stop here. So because the next section is the other topics we're gonna take into account. So we'll stop here, and next chapters we're gonna introduce the fatigue if this okay, so if this spring is appearing to fatigue or buckling, how should we deal with it? Okay. Okay, so we just stop here.